In our previous video, we talked about a multiplexer. We discussed 2 by 1 multiplexer and 4 to 1 multiplexer. I will just give you an highlight about the physical chip. So the multiplexer itself can be found in an integrated chip. And as you can see, we have the symbol of the 4 to 1 multiplexer, and we have the controls such as the select line. We have S1 and S0, which represent the two select lines. And when you look at the package view, and this package view for 4 to 1 multiplexer can be identified as 74153. So this is the chip that contain a 4 to 1 multiplexer operation. The second schematic we drew in our previous video is contained inside this IC chip. So you can see if you have to identify the input and the output, where D0 to D3, which represent the input, and Y represent the output, and S0 and S1 represent the select line. So depending on the select lines, it will select whichever input will be passed to the output. And we can see we have 1G and 2G. So 1G bar and 2G bar, they represent the enable pin. And when we want to enable, for example, in this chip, you can see there are two 4 to 1 multiplexer. So this D3, D2, D1, D0, they have the one in front, which represent the first 4 to 1 multiplexer, and 1Y represent the output. And on the other side, you can see 2D3, 2D2, 2D1, and 2D0. They now represent the second 4 by 1 MUX. And we have 2Y, which is the output of the second 4 to 1 multiplexer. So we have the select lines, which represent the control of this 4 to 1 multiplexer. So if we want to enable only one of the multiplexer, such that if we activate 1G1, that means this set of multiplexer will be in operation. And when we enable this one and disable 1G1, that means we enable the second 4 to 1 multiplexer to operate. So by enable, we are to select 1 or 0. If we say we select 1, where we apply a logic 1 to this first 4 to 1 multiplexer, then we enable the operation of this first 4 to 1 multiplexer. And if we apply 0, which means it is disabled. So if you want to use both of them, then you have to apply a logic 1 to both of this enable. That means this one should be enabled with a logic 1, 5 volts, so you can use both multiplexer. However, if you want to use only one multiplexer, you can enable one and disable the other. So this is the physical IC chip, where it has 16 pins. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So to identify which is the pin 1, we normally give the reference with respect to the chip, which is the kev. So this kev represent the header of the chip. So this represent the first pin of the chip. So that means this is pin 1. So you can just insert this chip on a breadboard, or if you have a PCB, you can just mount this IC and then applying your signal and the control signal, so it will produce the output. So that means VDD is the pin connected to a 5 volt supply, and pin 8 is the ground. So once you connect the voltage source to the chip and the ground, then you can connect the input and the output of the chip plus the enable. So this gives us a summary of what we discussed about a multiplexer circuit, where we have the multiple input and a single output. So when you think about a multiplexer, you can just think of a integrated circuit having multiple input and only a single output. And the control for the multiplexer is known as the select lines. So having that in mind, we are now going to introduce the demultiplexer. So demultiplexer can be simply known as the opposite of the multiplexer. And in that case, we should have a single input and multiple output. And in this case, we have the control. The control for a demultiplexer circuit is also the select lines. So in this video, we are now going to discuss a demultiplexer, and we will discuss 1 to 2 DEMUX. So DEMUX represent demultiplexer, and 1 to 4 DEMUX. So based on our discussion, we will look at the symbol, and we can look at the circuit diagram, and we can look at the Boolean expression and the truth table. So we now define what is a demultiplexer. So a demultiplexer is a combinational logic circuit. And since we are talking with a combinational logic circuit, we know that the input at that instant can be equals to the output at that instant without any delay. So a combinational logic circuit is a demultiplexer which takes in a single input and route it to a multiple output. So from this symbol, we can see a symbol of a demultiplexer, and the control is nothing but the select lines. Therefore, when we talk about a digital demultiplexer, we are talking about a demultiplexer that take in binary input and having binary output. Therefore, the select line will also be in terms of a binary. So why learning demultiplexer? So demultiplexer have some application in which it is critical. By knowing demultiplexer, we can apply in real life application, and most of the application is in the computer. So in a computer, we normally use demultiplexer in terms of storing the output of the arithmetic logic unit in multiple memory registers. So inside a computer, if you have your computer or your laptop or your mobile phone, you can be able to appreciate that most of the demultiplexer circuit can be found in these devices and distributing a single input to a multiple output. And in other case where we have the multiplexer circuit, and when the signal from a multiplexer circuit, if we want to have a DEMUX, where this single input can be passed to various output, Q0 to Qn, and we can say from those multiple input, I0 to In, we can pass through a single channel. And then when it passed through this single channel, we now be able to select which output it can be able to pass through. For example, if we pass the first input of a multiplexer, so this will become the output of the multiplexer. And if we want to store this particular input at different location, we have Q0, Q1, Q3. So this select line will select the first input of the multiplexer, and depend on the select line, it will store this information in the location Q3. When we talk about computer, it has a specific register, and this register can be seen as a memory circuit. And those type of input, we can select which of the register this input data will be stored. So in this case, this can be some application of a demultiplexer. And if you have a serial to maybe parallel converter, so we can have a demultiplexer as an input having serial data. So when we talk about serial data, that means all the data can be sent one at a time. For example, we have 101011. So this type of data is known as a serial data. And then when we have multiple output, and it can be represented as 101011. So those data are represented in terms of a parallel. So by looking at a demultiplexer, it is a system where we have serial data which can produce the parallel output. So with this understanding, we are now going to look at 1 to 2 demultiplexer in terms of the symbol, circuit diagram, expression, and the truth table. So we have now 1 to 2 DEMUX. So the symbol can have one input and two outputs. So Q0, Q1, and we have I1. So by understanding this symbol, we can generate the select lines. So by 2 to the n, where n represent the select lines, because this select lines is the control for the input and the output. And now when we have 2 to the power n, which will gives us the output. Previously, we look at 2 to the power n is equals to the input for the multiplexer. And now for the DEMUX, which we have 2 to the power n will be equals to the output. So for this case, if we have 2 to the power n is equals to 2 output, that means the n will be equals to 1. So we should have the select line, which is 1. So we can have S naught as our select line for this 1 to 2 DEMUX. So we can now be able to draw the circuit diagram when we know the actual number of output and we know the actual number of the select lines. The circuit diagram or the schematic can be drawn such that we have two AND gate and we have I naught, which is the input, and Q naught and Q1, which is the output. A NOT gate with the select line as NOT. So this is basically a simple circuit diagram for 1 to 2 DEMUX. So depending on this select line, it will select whether the input will pass through Q0 or Q1. And this output can be seen also as a channel. And this channel can lead to another devices. So this input data can be sent via the first channel or the second channel, or can be passed through a device which is connected to Q0 or a device connected to Q1. So if I have to maybe introduce the switch equivalent circuit, maybe the switch equivalent circuit can be drawn such that we have I naught and Q naught, or we have the Q1. So this switch can be transition between the two output, and this can be the select lines. So with this, we can be able to draw the truth table. So when we say when switch is 0, if we apply a 0 state at the select line, that means this second AND gate will be 0. And when we have 0 to any input, will still gives a 0. And this 0, after passing through a NOT gate, it will be 1. So that means we have 1 and we can have the input, which will gives us I naught. So from this, we can be able to deduce the truth table. And if we have 1 passing through the select lines, Now we know that this will be 1, so 1 with any of the input, which will still gives us I naught. So there are only two states, 1 and 0 for these select lines. So having this idea in mind, we can draw the truth table such that we have only one select line, let's say S naught, and we have output which is Q naught or Q1. So we can have 0 and 1. So when we say we apply 0 at the select line, so what will happen? Q naught will be equals to I naught and Q1 will be equals to 0. So when we apply a state 1 at the select line, that means the Q1 will have the value I naught and Q naught will be equals to 0. So in a simplified case, we can be able to say S naught, and we can say the output, and when it is 0 we can say Q naught is equals to I naught, and when it is 1 we can say Q1 is equals to I1. So those can be the truth table that represent the 1 to 2 demultiplexer. You might be able to come across some truth table which specify the input to a system and the output to a system. So I will discuss a little bit about this because they still have the same relationship. When you have the DEMUX and you have the Q naught and Q1, and when we talk about the input of the system, the entire input, we can have I naught and the select line S naught. So that means I naught and S naught, they are the input to the demultiplexer, and Q naught and Q1 is the output. So when we want to draw a truth table in a more general form, whatever we have discussed is in a simplified form, where this type of circuit, we can be able to find the combinational output, where we have 2 to the n, which will be equals to the combinational output. So when we have 2 to the 2, which is the input, number of input will gives us 4 combination. So we can say, comparing the input with the output, we can say that the input S naught and I naught, and the output is Q naught and Q1. So if we are to specify all the combinational input and the output, we know that it will be 4 as what is given in the equation. So we can have 0, 0, 0, 1, 1, 0, and 1, 1. So those are the combination of the input. So what will be the combinational output? So I will explain. When we have the input such that the S naught, the select line, is 0, and the input is also 0. That means this 0 represents that there are no data present in the data line such that the I naught. And from there we know that this will be 0 and this will be 0. And this will be 0 and the data line both having 0, and the select line, this one will gives us 1. So the output will be both having 0, although the select line, as mentioned previously, that will appear at the output. That means the data that will appear at the output I naught is equals to 0. That means no data. So we can see that this 2 will be 0 because no data is available at Q naught, and the Q1, which is by default not selected for data transmission. However, when we now have data from the input, that means we have 1, which is the data from the input, and the output is 0. That means this will be 0, this will be 1, and this will be 1, and the input is 1. So we know that the I naught will be equals to 1 at the output. Therefore, this will be 1, and by default, from the select lines, this will be 0. So this can be proved using our simplified truth table. When we have select line equals to 0, we have I naught. So previously, because I naught have no data, that means the output is also 0, because this represent no data and this represent having data for I naught. So you can see that when the select line is 0, that means we have the output I naught, which is 0. But this portion represent the input having no data, and this portion showing input having data. So the other case where we have the select line which is 1, however the input has no data, and that means the select line is 1, however the input is having no data. So now we have 1 here and 0, that means no data to the second AND gate, and the invert will be 0 and this will be 0. So by default this one will be 0 because the select line will disable the first AND gate and it will enable the second AND gate. However, the data from the input is 0. So by default, Q0 is 0 and Q1 is connected to the input. However, it has no data, so it will be 0. So we can say I0 is equals to 0 at output Q2. Now, when we have the select line which is still 1 and we have the data, so the input will have a data which represented by a 1, and now we should have 1 and 1 here, and by default this is 0 and 1. The output Q0 by default is 0, and the Q1 we have I0 is equals to 1. So Q1 will be equals to 1. So we can see that this represents the summary truth table that we produce when the select line is 1. That means in this case, select line is 1, it will select Q1 as an output. That means this region will be the output, and this by default won't allow any input data because it is disabled by the select line. And this represent having no data at the input, and this represent data available at the input and can be passed through the output. So the simplified version is like this, but in some other books you can be able to find this type of truth table, and this one represent a system connected like this, where we have compared the input and the output to a system. And to see the response of a system with regards to the equation, we now have two response, which is Q0 and Q1. So the equation can be, if looking at this truth table, we can say that the Q0 can be equivalent to S0 bar and I0. And for Q1, we can have S0, I0. So this can be the two equation that represent the response of the demultiplexer 1/2 DEMUX. And this is the simplified explanation that covers the symbol, the circuit diagram, and the truth table, and the equation for 1/2 demultiplexer. And by understanding this, we can continue to look at 1 to 2, 1 to 4, 1 to 8, 1 to 16, and all of these can be derived using this equation, where for the demultiplexer, we can have 2 to the power n, which will represent the output, and those output can be the number of output where this input can pass through. And when we look at the application, it is important that you learn the multiplexer in digital system, because it is found in many of the application, such as in a digital computer, in communication system, and you can apply this idea to your own set of research. If you are doing some research or doing some work in which you have one input and you want to pass this input to a number of output, then you can choose to use a demultiplexer circuit. So this type of circuit is known as the single input and multiple output system. And it is the opposite of a multiplexer, which is the multiple input and single output system. So we will continue on with our next video about 1 to 4 demultiplexer, where we describe a single input and we now should have 4 output. So if you like our video, you can kindly share with your friends so they can also be able to learn what is a demultiplexer. And also if you have some question, you can leave it in the comment section and I will answer them one by one.